Hello, and thank you for having me. My name is Andrew Janowczyk, and I'm an assistant research professor at Case Western Reserve University, a senior research scientist at the Lausanne University Hospital, and the secretary of the Swiss Digital Pathology Consortium. This brief talk will hopefully provide some background for our follow-up discussion on the topic of can I trust artificial intelligence and pathology? To begin, I think it's critical that we define some of the terminology that we'll be using here. In particular, I'd like to differentiate between general feature-based machine learning and two forms of deep learning. Here, machine learning will be defined as algorithms which accept features of different types of measurements, for example, nuclear morphology, texture, graph features, etc., and create a model by combining those features to predict a clinical variable of interest, such as diagnosis, prognosis, or therapy response. Typical algorithms of this class are things like random forest or XGBoost. Next, we have deep learning algorithms for detection and segmentation. These approaches accept a raw digital image and localize the object of interest, for example, circling the boundary of a tumor or a cancer cell. This class of algorithms is best exemplified by UNets. Lastly, we have end-to-end deep learning, which accepts a raw image and, similar to the segmentation approach above, will learn features, except this time with the goal of predicting the clinical variable of interest directly. For example, a ResNet that accepts an image and tries to predict whether or not that patient is going to respond to a particular therapy. So perhaps one of the motivating factors for this meeting is the realization that current deep learning technology appears brittle when testing on new data. Many, if not most, papers nowadays show that there's a significant drop in performance in deep learning classifiers when validating on data generated from an external site. Notably, this performance drop appears to occur both in segmentation and the end-to-end deep learning classes I mentioned above. We do have an understanding of why this happens and can be bundled into the term domain shift, which essentially means the properties of our testing data are different or shifted than the properties of the data we use to make our deep learning models. In digital pathology, this is mostly caused by pre-analytical variabilities, such as differences in scanners, brightness, stain variability, tissue thickness, etc. Essentially know that there are a lot of latent variables, perhaps even more than we can count, which contribute to the final presentation of a digital slide. It's worth pointing out that this domain shift performance drop still appears to happen even at larger scales. There have, of course, been approaches to try and ameliorate this problem, such as data augmentation and stain normalization, but they still don't quite get the performance of the classifier up to where it was originally when being evaluated on data generated at the same site. This begins to hint at one of the main concerns associated with deep learning. Since our models are entirely learned from the data itself, the data has to be of the utmost quality. Now, quality in this context doesn't simply mean, for example, not blurry, but more broadly that the pre-analytical variabilities are well accounted for. This can be especially challenging when we consider the potential for batch effects to be imparted on the data itself. For those unfamiliar, batch effects are changes in our input data that are unrelated to any biological factors and become especially dangerous when those differences are associated with the clinical variable of interest. I appreciate that that might be a bit much to digest, so I'll take a moment to give you a simple example. Let's say we have a data set and all of the patients with bad prognosis in that data set have overstained slides. Then it becomes possible for me to predict the prognosis of a patient simply by seeing if the slide is overstained or not. Clearly, this is a problem because I shouldn't be able to do that, yet I am. And yet the intelligence in artificial intelligence does not yet appreciate that this is a spurious association and should in fact be ignored. In fact, it's actually quite the opposite. It's much more likely to leverage this stain quality information when it's creating its model simply because it's so obvious of a signal for it to pick up on. How likely is this to happen in practice? Well, let me give you an example of a very likely situation. Let's say we create a tissue microarray of only high-risk patients and a second TMA with only low-risk patients. Now, any type of preparation difference between those two slides will result in a perfect separation of the classes. So if one slide was stained for just a little bit longer, it'll be just a little bit darker, and the deep learning algorithm will think that it's cracked this prognosis prediction problem when in fact it's only picked up on a very unintentional, subtle batch effect. As a result, one of the common requests that we have to receive and research that is continually being performed is this need for interpretability. Maybe we can motivate this a bit. If a model's prediction may be wrong due to latent variables, and these pre-analytical variables are very subtle and possibly not even visible by our human eye, then how can we trust the prediction that it gives us? Building off of that, when an algorithm does fail, since I know to date of no algorithm that's 100% accurate, who in fact is responsible for the failure of that algorithm and the potential downstream damage it may cause. So this is perhaps part of the conversation today to say that there's no such thing as a bad algorithm. Maybe there's only dangerous workflows which use that algorithm. So let's take a look at two types of workflows and compare and contrast them. In example one, we have an algorithm that highlights an area, for example, of a tumor, and asks the pathologist if they agree. If the pathologist agrees, then the algorithm can precisely measure that tumor area. In example two, the algorithm examines a whole slide image and predicts the genotype or risk of recurrence for that patient. In this case of genotyping, we can still use DNA sequencing to verify that the prediction is correct, but not knowing which patients need that verification may result in us having to verify them all. This may be worse in the prediction of recurrence risk if there isn't an established biomarker that we can use for validation or as a ground truth. Although in both cases, we don't have a clear understanding of how the algorithm is performing its task, at least in the first task, it has the ability to be visually verified. So if the algorithm is completely wrong, the user will immediately realize this when looking at the results and know to ignore them, essentially creating a strong backstop preventing any negative actions from taking place as a result of algorithm failure. Use cases that we're starting to see emerge as a result of this concept are exemplified by this recent Lancet Digital Health paper, which is looking at using deep learning to highlight prostate cancer in biopsies. Interestingly, they are using this tool as a second reader for quality control. This means that a pathologist simply goes about their routine day-to-day work unaided by the algorithm. In the background, however, this algorithm is acting as a second reader to quality control 100% of the cases to make sure that there's no shocking difference between the human and the deep learning derived diagnosis. Again, this hopefully creates a situation where it's very unlikely for something to go wrong because the pathologist is performing their work in established workflows and simply receives the benefit in the rare case that they might make an error, that now it can be identified and reviewed. Now, there are folks that may want to say, well, shouldn't it be possible for algorithms to be run first and highlight the regions for review later, under the guise that they don't have to, for example, look at an entire slide set for a particular case? One potential concern here is that there's already evidence of something called automation bias, which is essentially a psychological human barrier that humans appear to create during against disagreeing with an algorithm. Think of it this way. You know that an algorithm is said to be 99% of the time correct, and it happens to have a different diagnosis than you. What situation does that put you in? Please note, I'm not trying to call out a single instance where this happens, because I know that we already have well-established ways of dealing with this. For example, calling in a consultation or requesting additional tests. I'm speaking about the long-term impact if this algorithm is consistently shown to be correct. Does there come a point where you start to second-guess your own judgment and simply rubber stamp the algorithm's result? Also, if you do finally override the algorithm's suggestion and it turns out that you were incorrect, what is the legal consequences for that decision? And if those legal consequences are very severe, are you more or less likely to simply accept the output from the algorithm in the future? There's also this concept of alert fatigue, where if people are constantly alerted about something, naturally their brains begin to mentally suppress that alert. So if your algorithm isn't accurate enough, you could in theory implement it in a workflow, and after a few incorrect alerts, the user will simply begin to ignore it entirely. Where is that threshold where that actually happens? We simply don't know yet. So these are some of the open questions in terms of not algorithm performance, but how do humans react when interacting with these algorithms? One of the reasons we don't have these clear answers to these questions yet is simply because we have never had sufficiently powerful algorithms to begin their study. But of course, this is very likely to change now and in the near future. Lastly, some additional places for research and improvement. If we know that latent variables affect the performance of these algorithms, it makes sense to try and control for them. This can happen on two fronts. Lab managers can be informed as to what good quality slides look like and begin to refine their slide creation process to match those standards. On the second front, algorithm developers should explicitly define the range of values for which their algorithm has been validated. For example, if they have only tested their model on images falling in this part of the brightness distribution, then when a new slide comes in that is outside of that range, a red flag should be raised indicating that the results may not be reliable. To that end, we have built a tool which works quite well in that regard, measuring these properties, and have made it freely available at histoqc.com. And finally, a component that's only now starting to emerge is providing confidence estimates for model predictions. Now, please note here that this goes far beyond simply looking at the last layer of a deep learning network and using that as a surrogate for confidence. I could give a whole talk alone about how that fails for a number of reasons, but I'd like to give you a bit of a contrived example to think about. If I have a tumor versus non-tumor classifier, and somehow accidentally a picture of this cat gets submitted for diagnosis, today most of the models will tell you ideally that this cat is not a tumor. At the same time, hopefully this triggers an uncomfortable type feeling in your mind, because what you really want is your algorithm to say, hey, something's wrong, I have no idea what this is or how to address it. So essentially to have algorithms realize that they are out of their depth and reject the entire premise of the question. That would already lead to a better sense of trust in the performance of these algorithms. So that concludes my talk, and I'm eager to start the discussion. Thank you.